that the backend can do something with these types, because they are still Python types. They are lists and dictionaries and whatnot. And the backend cannot. I mean, in C, there's no such thing as a list and as a dictionary. So you have to transform these types into to fit the type of the backend. And right now we have two type systems. There's the LL type system and the OO type system. The LL type system is a type system that fits to like C, very low-level languages like C, and currently we also target LLVM, which is a low-level virtual machine. It's a very interesting project too. And the LL type system contains types such as you have structures and arrays and pointers and function pointers and the usual stuff that you find in C. And then we have the OO type system to target object-oriented languages like Java and JavaScript, Smalltalk. And the idea there is that you have classes and instances, and you can call methods and all that usual stuff. And after this specialization step, you have specialized flow graphs that contain only operations that fit the backend, like fit C, for example. And now we come to the backends. The backends start at where the specialization left off. We have a specialized flow graph, and the backend basically takes these and produces code in the target language. Currently, we have two complete backends, which is C and LLVM. And we are currently working on two more backends. One of them is JavaScript backend, which also kind of works for medium-sized examples already. And we have a Squeak backend that we're currently working on. And in these backends, you also have to support foreign function calls, like stuff that really can only be implemented in the operating system. And for that, you need small, very small, manually written code snippets. And yeah, I think all in all, we have a couple of hundred lines of C code in the whole project. So, and now we are going to.
You set this up, and I ask if somebody has questions. Yep. So until here, now we're going to show larger examples of all these flow graphs and code generation. Are there some fundamental questions already that you want to ask?
You mentioned porting some of the built-ins from C to Python. I was wondering if you talked about your experience in doing that. Did they get shorter? Did they get simpler? Did you find bugs?
Oh yes. So that was we did actually find a lot of bugs, and especially in the parser and compiler, which we took from CPython, the compiler package. It basically delayed some of our project for 1 or 2 months because we had to fix a lot of bugs basically in there. And also when porting things from C to Python, it gets a lot simpler. So all the built-in functions and all the, also part of the I/O handling and all this is a lot easier to read basically. And there were a couple of bugs fixed and also backported to CPython even. So basically there's some stuff already that is back into CPython that came from pypy.
I think it's also, in generally, we tend to find lots of bugs in CPython. I mean, we have found within the project something like 4 or 5 seg faults in CPython, which is something that regularly should never happen. But you try to find out some obscure detail and crash CPython's down. And okay, another one or yes? Do you want to try it? Or tell me, I'm going to tell. How do we find a fixed point? That's a tricky question because it's really. Sorry? Well, this is really a difficult question. The question was, how do we know whether we have found the fixed point, whether the variable does not get more general anymore? And basically, the general idea is we know that the change of one variable affects another variable. So we reach a fixed point if something changes, we generalize the variables that depend on that change again. And just at one point, there will be no changes left that need to be propagated. And I mean, it's really getting a bit too detailed into the how annotation works. But if you want to, we can discuss this. Yeah, of course. I mean, the point is we go only from special to general. We never go in the opposite direction. So it's certain that we will reach a fixed point. Okay, to this example, it's the function that we have already seen. we loop over the length of the list and sum the elements. And here, the list, which you can see here. Oh, one moment. Yes. On the bottom, you can see the types that were inferred for the function. Here, for this sequence, the annotator knows that.
You want to have full equipment now?
Oh, cool. For this sequence, the annotator knows that it's a list, and it's a list that contains only integers. And, well, it doesn't help because I need this. And then we call the len of this sequence, and the result, the length of the sequence is an integer. And then we call a range, which is again a list which contains only integers, and then we iterate over that. And maybe I can zoom out. Yes, here you see basically the full flow graph of the function. You see here is the loop. You loop here until you're finished, and then go out there. This is the return block where the return value is put back to the, oops. Okay, basically here you construct the iterator, which is, well, some iterator. And here you call next on it, which returns an int. Yep. And here you perform the get item. You get the v5 item, out of the sequence, which is stored in the variable v6. And then we add v7 and v6 to v8, which is then flown into this block back again. Then you go back here for a while until at one point where the iteration stops. The stop iteration exception is erased, and you end up here. And you can see that, one point you can see is that here you add an int and an int, and the result is again an integer, of course. And in the end, you can also see that the return type of the value is also an integer. So this was after flow graph construction and annotation, type inference. Now we're going to look at the flow graph after specialization. Oh, good. 1 second. It's now generating flow graphs, performing type inference and specialization, and it's now creating code and now compiling, and it's finished. So it's a rather small example, so it's rather fast. We have again the sum function here. Oops. Okay, this takes a while for obscure reasons.
Yes,
good.
Well, the thing is maybe
It takes a second. The problem is we need network access for obscure reasons.
Explain the obscure reason.
Yeah, you can.
Okay, the obscure reason in 20 seconds. The obscure reason is that the GraphViz library is broken since, I don't know, half a year, because we generate these huge flow graphs. There's some syntax in there that breaks it. And we also submitted a patch, I think half a year ago, but it didn't get accepted. So we have a server in the network that if GraphViz crashes, we contact via HTTP this server, have the patched version there, send the stuff back. Because we don't want to require everyone who uses this. You just can install standard components. We don't want to require everyone to install a patched version of a library, right? Okay, so we have a very practical approaches to certain problems.
Of course, it can take an arbitrarily long time, especially if the connection is bad. And therefore, we will maybe look at the generated C source first. And let me just warn you, the generated C source is very scary. There. Yes, good. So first at this. Basically, you now have, yes, that's a specialized flow graph, so it's specialized for C. You now have stuff like signed, which is not just an integer, it's a signed integer. And you have a pointer to a GC struct range, which contains a start, which is signed, and stop, which is signed. And you call function pointers here. This is a function pointer to something. And you pass in stuff. And then you have the same structure of the flow graph, but the operations, down there, you cannot see it because it's too small. But down here, you have something like int add. Here you have incorporated the information that these two variables are ints, so you add an int. And the return is again assigned, and that gets returned. And I also want to look at the source code. As I said, it's kind of scary. We produce pages and pages of stuff. Yeah, of course, you would write it like that too. And here you have, in the end, the function. It basically, the blocks, I mean, it's not mapped to any control construct anymore. You just have blocks, and you have go-tos between the blocks. And here you call new range and range iter, which you see, no, not here, but nowhere. For the function itself? No, never mind. Basically, here you have the first block, and then here you have the loop. Basically, where is it? The add is somewhere too. It's really a bit hard to navigate. But it's usually never looked at, so we don't care. Yep, here's the add. And above it is the get item. Here you get the item out of the list, and then you start adding, and at the end you return here. Okay? No, where were we? Here. So now we come to a very important and very, oh, I have to speed up, right? Okay, we have a very important concept within pypy, and this is one of the concepts that makes pypy quite different from other language implementations. And the idea is that we want to make implementations decisions for the implementation of the interpreter very late. For example, what GC are we going to use? What threading models are we going to use? What calling convention are we going to use? The idea is to make it not at all, make these decisions not at all during the interpreter implementation. This is not true, for example, in CPython, their reference counting is used. That means at every point in every file of CPython, you see that you use reference counting, because all the time you have ingraph, degraph, ingraph, degraph. You need to be very careful to not make mistakes there. We don't make this decision at all. Nowhere in our interpreter you will find an idea what GC we are going to use. So the idea is that these decisions are then later at translation time weaved into the implementation. So we take this RPython implementation of a Python interpreter, translate it to C, and weave certain aspects in. And one aspect is we can choose what GC we are going to use. And it's very important, this is completely independent of what language we're implementing. And currently we're implementing a Python interpreter. But if we implement in our Python, whatever Lua interpreter, we could weave in the same manner different GCs, different threading models, and so on. Thanks. For one of the aspects we're really targeting is memory models. Currently we have implemented two different garbage collectors. One of them is ref counting because it's very easy. The other one is just to use the boom collector, which is also very easy, which is a very tuned garbage collector, conservative garbage collector for C. And we're currently working on more general and exact GCs, which will also be written in Python. And there's a framework for it there, but it's not yet integrated into the rest, so you cannot use it in pypy, but it's on its way. And we have implemented a copying garbage collector and a mark and sweep garbage collector, and possibilities to do much more and sophisticated algorithms. Okay. Then another important translation aspect is threading model. Currently, we have the very important choice to have no threading, because threading sucks. And you have the choice to have a global interpreter lock, which is the same technique that CPython uses. Basically, you have a lock so that at one point only one Python program can be interpreted, which is not optimal, but anyway. And in the future, we plan to implement as a translation aspect more free threading models with more fine-grained locking. And another aspect that's related to threading models is stacklessness. Christian Tismer wrote the stackless. Raise your hand. Christian Tismer wrote the stackless patch to CPython, which is basically a patch to not map Python user level recursion to the C stack. So you can have in an interpreted program arbitrarily deep recursion until your heap runs out, and this is not reflected in that your C stack is growing and growing. And we can also translate our interpreter into a